Uh, Let us just have a very quick recap with few questionnaires. My question to you is that if you want a long distance uh, wire that has to be integrated to your controller, okay, so what kind of loop are you going to give to the sensor? Whether it will be a current loop or whether it will be a voltage loop for analog input. Yes, it will be a current loop. Okay, okay. It will be a current loop. Yes, okay. Normally for digital sensors, which has only digital output and inputs, what kind of loop is preferable? Voltage or current? External voltage is applied to the sensor. Next question will be whether the external voltage is supplied to the sensor or not. For our photoelectric sensors, we have seen the example of photoelectric sensors, right? So my question to you is that whether external voltage was applied to those sensors or not. Okay. So my next question to you is that when you are integrating a particular sensor, okay, so if there is a conveyor and material is non-metallic, then what kind of sensor would you prefer? An inductive one, a photoelectric one, or something else? Yes, capacitive sensors can be the answer. Correct, correct, Rajnandini. Other answers, please. Others kindly respond to the question. A very easy question. Class, kindly respond. Let me repeat the question. Then, if the material at the conveyor that is flowing is non-metallic, what kind of sensor would you prefer? Inductive or something else? Your answers, Hitesh, Sunidhi, Hitendra, Khushbu, Bhanu. Class, your answers, please. Yeah, Bhanu answered inductive. Capacitive, yes. Photoelectric can be the answer. Bhanu, why inductive sensor for non-metallic part? Yes, yes. It might be capacitive. It might be photoelectric. It depends on the due to high switching frequency. But inductive sensors don't work with the non-metallic material, right? Am I right or wrong, Bhanu? So inductive sensor is not a correct answer because I was using the statement that was non-metallic material that is flowing through the conveyor. Okay. So now, yeah, yeah, yes.
Hello.
Yeah, Banu, yeah.
Sir, earlier you have asked confusion that whether we can use inductive sensors for non-metallic objects, and then we all replied yes at that time. And you
That
said that it was okay.
I don't memorize that, but um, had I said that inductive sensors can be used for non-metallic part, I think I had not.
Yes, sir. At that time,
I think there might be some confusion. I would have said for
I
capacity.
was.
There might be some. Okay, it might be some thing different than what you have understood, or I would have understood. But that is for sure that inductive sensors can't be used for non-metallic part. They can be used for metallic part. I think I have used some another example. I think for capacitive, it was asked that whether the capacitives can be used for metallic part or not. Yes, capacitive can be used for metallic part and non-metallic part both, but we prefer inductive for metallic part.
Oh, this was the point, sir. I thought in other sense.
And that was reverse. So Nidhi, am I correct? Adarsh, am I correct? I asked for capacitive and I asked that whether we can use capacitive for metallic part. We said that yes, we can use it, but inductive we prefer for metallic part. Am I correct? Adarsh and Sunidhi, can we be on the same page for that? For all students, are we on the same page on this? Yeah. So Bhanu, there might be some confusion from your end or from my end, but let us be on same page.
Confusion from my side. Yeah. I
Yeah,
was confused a little bit.
yeah. So that might be from someone's end. It doesn't matter, but the clear picture should be in front of all of us. And the clear picture is that inductive sensors can only be used for metallic parts. Okay, whereas capacitive can be used for metallic part as well as non-metallic part. But because of high frequency, we use inductive. We prefer inductive sensors for metallic objects. Okay. I think now we are on the same page. Okay. Okay. Now let us continue. Let me just share the videos that the list of videos or the link that I will share this consolidated Word document to you. I have just mentioned. Let me just share my screen and let me just share this Word document also with you. Just a minute. Yeah, is my screen visible to all of you? Yeah, yes. So what I have done in a previous class, I have provided you few videos and now I'm giving you the link for these 14 videos. Why I'm doing this is that I will send you this consolidated Word document for once only. Okay, in the end of the session, I will share you with this. I will share you this document where I have noted the procedure, or you can say just a single line about the video, and I am just taking the line of videos that we are taking. Okay, so it will be very easy for you to recap and to get your confusions clear. So there is a topic that has been associated with this particular link, and that will be very easy for you. Okay, so you can also just create your document of your own. I've sent you the links on the chat box. Till 5 they have been added because there is a word limit. Till 7 I have already given you, right? So I will just give this from, okay, from 5 only I will give. 10. Let me just see. 6, 7, 8, 9, 10, 11. Yes, from 11. Okay. So these are the links. You can access these links anytime if you want for your lectures. Okay, and I will just share this particular document with you. Okay, so now I think we are aligned on this. We also know that what sensors basically are. And can we have a very quick recap of that PPT that I was showing about the basic working principle? I think you all are very much into that. You learn a lot of that stuff from your theoretical classes, I think. So I wanted to skip that. Should I skip that or should I continue? Can you answer skip or continue? That part, let me again show you that part and then you can answer, because that depends on you. Or we can just have a very quick review of these sensors, that what is the basic principle of what sensor. These PPTs about capacitive, differential, eddy current, inductive, pneumatic sensor, optical encoder, proximity, reed switch, Hall effect, tacho generator, pyroelectric, and tactile sensors. So should I give you a brief about it or should I skip this? A very little brief, quick review. Okay. A quick review will work. Okay. I will give you the quick review of this particular PPT, but before that, we should continue with the single video that was left. I already told you that I am going to give you a example of an industry grade, you can say technical session, and that is related to the fundamental of your sensors, and we are going to continue with that only. Okay, just have a, it's a 50-minute video, but have a very detailed look to this. Okay, I will, we will have some questionnaires so that you can just understand that what they are trying to convey. It is just on the basic fundamentals of 4 to 20 milliamp current loops. Okay, but it is very important that the kind of message that they are going to convey. Okay, so just kindly focus on this. Okay, if you have any issue, okay, we can repeat that particular session from that particular part. Okay, there is going to be no issue regarding that, but have a very brief review and very what we say detailed review about it. Okay, so let us just look at this. You can just have a quick review that this is a transmitter, this is a power source, and this is a receiver. Okay, that receives and interprets the current signal. Okay, and then you get the answers. Okay, now just let us move towards this video.
We deal with. Welcome, folks. Is will I get an easy? Will
let me skip the other.
I'm your moderator today, and I'm speaking to you from Boulder, Colorado.
Just spot if a 4 to 20 milliamp loop is the fundamentals of the four.
Introductions ahead. I'm going to turn it over to Joe to kick off what we'll be covering today. Joe?
All right. Thank you, Bruce. So first, why don't we take a look at what our objectives and takeaways are for our webinar today. We're really hoping that you leave here with an understanding of three things. The first of which, obviously, is the fundamentals of the 4 to 20 milliamp current loop. That's what is a current loop? Why is it 4 to 20 milliamps? What are the things you have to be aware of in order to work with it? We want you to be able to choose the correct devices and instruments that go into that current loop. There's specific devices that are always going to be present in a current loop in order to make it happen. And you need to have an understanding of what those are if you're going to.
Okay, so we had a very brief discussion about yeah, so we already had a very brief discussion about 4 to 20 milliamp. This video is visible and the audio is quite audible, right? There is no issue in this video. And if it is correct, I have just a very small question before I start with these objective and key takeaways from this video. We understood about 4 to 20 milliamp current loops a little bit. and we understand that how much important it is for an analog sensor to run in a particular manner, that it is current controlled loop, and since current is equal in all the circuit, therefore that is one of the major reason. Am I correct or not? First question is this, and my second question is that we have a very preliminary idea about that how can we be able to choose whether we should use a voltage loop or a current loop. Okay, we have that preliminary idea? Yes or no? Yes. Okay. Okay. We have a very little idea, but let us go into the brief and more descriptions that Mr. Rihan is going to teach us. And it is a very technical session, and this has been uh, resourced from your Precision Digital, which is one of the best sensor making companies, and related to all the sensor works. It is one of the pioneer in this industry. Okay, so just take, and that is a pro bono case where they are dealing with this. You have to deal with these kind of sessions when you go into industries. Therefore, I just wanted to give you a particular look. Okay, so you will have some people who are uh, much more into a single technology, and they know very much about that. But for that, in order to attain maximum out of a particular technical session, you should understand that how the procedure goes, how they want to teach about the insight of a particular technology. Uh, just have a brief look about that also. Okay, not just about the fundamentals of 4 to 20 million, but how in industries a particular technical session works. In most of the industries, the technical session works like this only. Okay, let us continue without wasting much time.
Going to be able to work with current loops. And the last one is being able to spot if a 4 to 20 milliamp loop is the right choice for your process need. It's an industrial standard that's extremely common out there, but it's not great for every application. And some applications that should be 4 to 20 loops may be currently being used as something else. So to do that, we're going to follow the agenda you see here. We're going to define the 4 to 20 milliamp current loop. Again, a discussion of what that actually means. We're going to discuss the individual components at length. We're going to review the pros and cons so that you'll know why people use it, but also why sometimes they don't. And we'll let you know what the essentials are you should walk away here from, so that if nothing else, you can know what to keep an eye out for when you're out there in these process applications and you have the opportunity to work with a 4 to 20 loop. But Bruce, before we get into the content, you had a few questions.
Yeah. I know on webinars it seems like you may be the only one listening.
These are
but
just the
I think
questions.
it's
Let
to
us
start
skip
off
this.
with.
He's asking just.
Joe tweaked the presentation a little bit. He knows what the general knowledge.
Yeah, now you can see that there are seasonal field experts also. Okay, there are a few electrical engineers, and they are enough to get the job done. Okay, so most of these are associated to the process field jobs only. Okay, so
Colleges out there. We get too many. It's like about half.
Well, it's a current thought about in a while.
okay, let us start from here now. Okay, I have just skipped that part. That was just a questionnaire from companies, and that from where the people were associated, and from the at what part of the country they were.
So let's dive right into the content here. With what is a 4 to 20 milliamp current loop? Well, it's a current loop, obviously. And in order to understand how that current loop works, I want to touch on the only equation we'll talk about here today, which is V equals IR. And that's the fundamental electrical engineering equation, that voltage is equal to current times resistance. So anytime you have one You want to have all of those, and this explains how they interact with one another. Now, the important thing to understand about these is how they interact in a circuit. So we've got a very basic circuit diagram up here. On the left of the diagram, I've got my VTOT, and that represents what's providing the voltage to make this circuit run. In most cases in the process industry, you're going to find that that's going to be a DC power supply of some kind, although it could also be a battery or any other voltage source. Then I've got the different elements that are connected up in my current loop. I've got R1, R2, and R3, which are modeled as resistors, but really could be any kind of load. That could be a panel meter or a PLC. It could be a transmitter, a chart recorder, anything that is connected up to that loop. Each one of those devices, because it has a unique R, is going to have its own voltage drop. So my VTOT is my power supply giving the voltage to the loop, and then I lose voltage at R1, R2, and R3. The critical thing to understanding why the current loop is so popular and how to wire it up is that you'll see there's only one I, and that's the dashed looped arrow running through the middle of this circuit. I is the same everywhere. Every element here has a different resistance or impedance, and every element has a different voltage drop or is providing the voltage, but the current is the same anywhere. So if I measure that current between VTOT and V1 in this circuit, it's the same as if I measured it in between V2 and V3. And that's the big strength of this current loop, which we'll discuss in a little bit. One convenient way to think about current loops and circuits in general is in a flow analogy, which is something that a lot of people have a much more intuitive understanding of. In this circuit on the left, my VTOT is the power supply, which can be modeled as the equivalent of a pressurized water tank, and that's what you see here in the picture. The resistors, the loads on the circuit, can be modeled as, for example, we've just got a simple water wheel here. It could also be modeled as a pipe restriction, or any other element in the flow system that's going to impede the flow of that water trying to leave the tank. The current is essentially the flow of water. So I've got this potential built up in my pressurized tank. The water's trying to escape. It wants to equalize down to zero pressure everywhere, but it's hitting these restrictive points like the water wheel, where I'm going to have water pressure backed up on one side and not the other. So with pressure being my voltage, you can see where I would get a pressure drop on each side of that water wheel. The pressures would be different, but the flow throughout the pipe's the same. The same water I have going into the pipe from the tank is the same flow of water I have pouring out the bottom of the pipe after the water wheel. So current's the same everywhere in this circuit, even though I've got different voltage drops across the different resistive elements. With that basic explanation out of the way, let's talk a little bit about how we got to where we are and why people use this. This technology, the 4-to-20 loop, started appearing in the 1950s. It was influenced heavily by the pneumatic systems that existed at the time. Those generally would use compressed air as a control, and everything would be mechanical. You would have pressurized air tubes running all throughout your plant, controlling your processes and transmitting that information. Those usually would be in the range of 3 to 15 psi, though it could vary. And much like the 4 to 20 milliamp signal, you'll notice there's no zero there. And there's two reasons for that. The first is that modeling a 0 milliamp output from something was very difficult to do. While it's easy to get 0 milliamps, it's an open circuit where there's no current flow at all. The problem is the low ranges. Trying to get something that could sweep from, say, 20 milliamps all the way down to zero, passing through the 1 milliamp, the 0.5 milliamps, the 0.1 milliamps. Designing the circuitry to do that was very difficult and expensive, especially back then. The other reason, and this is something that the pneumatic systems took advantage of, and 4-to-20 just decided to do the same, is that by making your 0% signal 4 milliamps, you know when the difference is between, or you know what the difference is between a 0% signal and some kind of failure in your system. So if I have 0 milliamps on my line, or I have 1 milliamp on my line, I know I have some kind of problem. I have a device that's wired wrong. I have a break in my line. Something is going haywire, because even at 0, I should be seeing 4 milliamps. If I had that 0 to 20 milliamp range, then I may think that my system is just off and I'm getting a 0% signal, but in reality, someone's broken a wire, or I've lost power, or there's been some kind of other failure. If you find this topic fascinating and you want to do a little bit more reading on it, you can find the industrial specification up on your screen. And I'd encourage those of you who really want to dive into this to go take a look at that.
Yeah. So class, my question to you is again, this is just I think 1/4 part of this session. I have few questions related to it. Okay. So what is the biggest strength of current loop? What is the biggest strength of current loop as per Mr. Ryan? Current is same. I need answers from all of you. Answer might be repetitive, but I need answer from all of you. Yeah. So the strength for the, okay. So you have an, okay. And you can say that V total, V total was distributed into many resistance R1, R2, R3, and these R1, R2, R3 can be what? What can be those R1, R2, R3? They can be loads, but what kind of load they can be? Can you name few? Resistance are load, but what kind of load? What kind of load? Yeah, such in PLC, transmitter, your recorder, okay? Your PLC, your transmitter, your recorder, okay? So now you understood a very, your solenoid also can be a part of that. But actually what we do is that if we are taking, Shubham, we are talking about a sensor, okay? So sensor is going to give you a sense, okay, and that it might be converting it into a voltage signal through transmitter only, okay? So there will be a PLC transmitter, okay, and then it will be giving it to a controller, okay, and in controller there might be a recorder, okay, which records it or collects it, okay? So these kind of load can work, Shubham, because we are talking about a sensor, okay? We are talking about a 4 to 20 milliamp for a particular sensor, okay? Shubham, did you get it? Okay. Excuse me. So your total voltage can be distributed amongst transmitter, it can be distributed among PLC, but current is same throughout the loop. That is why you use 4 to 20 milliamp. Okay, so this 4 to 20 milliamp technology started in 1950. Yeah, 1950. Okay, and what was used before 1950? What kind of technology was used before 1950 for control loops? What kind of technology was used which was prominent? Yes, pneumatics. Compressed. Yes, very correct, Adarsh Shukla. That was compressed here, which is your pneumatics. Okay. And they also said that 0 is not practical. Why is 0 not practical? Yeah, ये वाले में कर लूँगा. ये वाला है. Why is 0 current not practical? There are two reasons for that. They were talking about that why 0 is not Okay, so let me repeat that for you. First reason was that modeling zero is difficult. Yeah, won't able to confirm that there is breakdown. Yes, for that parameter should be identical. Okay, uh, okay, and also modeling a zero circuit is very difficult. Why it is difficult? Because it is tough to maintain a such low voltage. Okay, so from 0 you need 0.1, 0.2 or 0.01. In order to maintain that, it is very difficult for maintaining it regularly. Okay, without a circuit break. Okay, first thing was that it is very difficult to model a zero. Okay, and second reason was that 0% signal would have been confused with a breakdown. We will be Adarsh has said it right that we won't be able to confirm that there is a breakdown, or for that parameter should be identical. Okay, 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 good. So let us now continue with other part also.
Although it's not particularly engaging reading. So what is a 4 to 20 milliamp current?
In class, just draw this particular signal, okay, on your notebook, and you can use just a block for this process controller, but draw this entire circuit, okay, just like a block, and send it through WhatsApp, okay, on your on our group, okay. And this exercise is very much necessary so that this circuit can be infused into your minds. Okay, so just draw it for once and show it on to me on the WhatsApp group. Just a minute. Class, just draw it in block form only. Okay, no need to draw the exact drawing of your transmitter and recorder. Okay, just draw it through block diagrams only. The uh, circuitry is very much important for you to understand. Okay. I got the photograph from only 2 students. Class, I think this should not take that much time. Be a little bit quick. Okay. Yeah, so class, most of you have drawn this circuit. Now let us have a brief, you can say summary. That now you can see that your sensor is not just a sensor. It is going to give you a physical change. It is just going to sense a particular physical change and change its property. Now this property change is infused into the circuit through a transmitter, whether the change in resistance, or you can say another parameter that has been added to this. Okay, but this loop is going to be same. Okay, and this loop is going to be a current loop, and that particular value that is moving in a particular loop will be, you can say, recorded through here. Okay, now it can be recorded through current only. This is going to go into a particular process controller, you can say, which will display it. Now you can say that it is going into a current form. Now this minus has been connected to plus, plus has been connected to minus, this plus is plus, this minus is minus. Okay, just have a quick look into this, that you can see that current is moving from this particular direction. Okay, and moving towards this particular direction. Now you can see that this is changing. Okay, this will change the characteristic current within the circuit. Okay, but throughout the loop that current is going to be same. Okay, so now you can see that this, earlier what I was talking about was comparative value. Okay, so that comparative value is always going to be same throughout a loop. For a particular instance, that value is going to be same. The value of current is going to although change with the change of property of the sensor, but that comparison will not be changed and will not drop among the circuit, whether it is for longer wire or shorter wire, it will not matter. That is the reason that we use this 4 to 20 milliamp circuit. Okay, so let us continue with this.
Current loop in terms of a process control loop, let's say. Well, you have to understand the different components that make it up. And the first one's going to be the sensor, which is that thing that's providing some kind of output based on your actual measured process variable. It actually is in contact with the material that's going through a flow meter, or it's the thermocouple connected to whatever the temperature is being read from. You've got a transmitter. The transmitter is what's responsible for actually creating that 4 to 20 milliamp signal and regulating it. And then you've got some kind of receiver or multiple receivers. In the graphic here, we've got it being a process controller, but it could be any number of devices. The last element is the power supply, which may or may not be an entirely separate device. And I'm going to go a little bit more into detail on each of these now so that you can have a better understanding of how these all interact. The first element is the sensor. This isn't actually part of the 4 to 20 milliamp current loop itself, but obviously it's a critical component. This is what's actually measuring whatever it is you're trying to provide a 4 to 20 milliamp output from. In the case of a flow system, this could be a turbine flow meter that would provide a small millivolt pulse output. It could be a thermocouple or an RTD that's in contact with something reading the temperature. It could be the optical encoder that's reading pulse outputs from something that spins, or it could be the actual ultrasonic emitters on an ultrasonic level transmitter. So it's the often unique and specialized technology that's getting you your process variable into your electrical system. Generally, they'll do that by outputting some kind of voltage. And in that case, okay, you could just try to use the voltage instead of a 4 to 20 loop. But there's a lot of issues. Can it run before the resistance of the wire becomes a problem? How affected is it going to be by noise? Is it a useful signal at all? And in some cases, the signals are so small and so subject to outside interference that you really couldn't do anything with it anyway. Systems such as radar level readings really need to be transmitted out as something else in order for them to be fully understood. They have to have complicated timing circuits in there. So the sensor can be fairly complicated or pretty simple, but it's never ideal to work with that signal being output. And that's really where your transmitter comes in. The transmitter and the sensor are often the same thing, although sometimes they are different components. You could have a separate thermocouple and a temperature transmitter, for example, that are two different things that could be bought separately, but you could also have a radar level gauge or radar level transmitter, the one device you purchase. The purpose of the transmitter is to take that unique signal that's measuring your process variable and use it to regulate the 4 to 20 milliamp signal. So what the transmitter does is say, all right, well, it's developed so that at 0% of whatever its measurement range is, you're going to get 4 milliamps. And at 100% of whatever its measurement range is, you're going to get 20 milliamps. Most of the time, those 2 points are connected by just a simple linear line. So if I'm looking at the scaling example shown here, I would have a level transmitter that's designed for 100 feet. And when I'm at 0 feet, my level transmitter is going to be outputting 4 milliamps. When my level transmitter is detecting that there's 100 feet, it's going to be outputting 20 milliamps. And then it just connects all the points in between. So if I'm at 50 feet in this tank that I have this transmitter on, it's going to be outputting a 12 milliamp signal. The transmitter regulates the current in the loop. The power supply is what provides the voltage to make that current possible. Because remember, your V equals IR. In order to have a current there, you've got to have a voltage. This is always going to be a DC power supply. When you hear 4 to 20 milliamps, what they really mean is 4 to 20 milliamps DC. And in most process applications, people use a 24-volt power supply simply because it's the most common and convenient. You could run into others, though. There's 9, 12, 15, 36 volts. There's probably some other oddballs out there that you'll run into as well. But the idea here is that all they're doing is providing the DC voltage. They're not regulating the current. That's the job of the transmitter. The critical part about the power supply is that whatever voltage you're providing, it needs to be higher than the sum of the voltage drops in all the other elements of the loop. Usually that's not a problem. If you don't work with any 2-wire or loop-powered devices, you may not even have to worry about this. You may not even think about it in your day-to-day affairs. However, if you're using 2-wire or loop-powered devices, this becomes really critical. You want to make sure that you're not using a 2-wire transmitter, meaning that it draws its power off of the current loop. And that transmitter might require an 18-volt drop, but then trying to run it with a 9-volt power supply. Because regardless of how small the voltage drops may be in all those other pieces of equipment, that 18 volts in your transmitter is going to sink that 9-volt supply, and now all of a sudden your system's not going to work. So it's critical, especially in cases where you're involving 2-wire devices, that you know what your voltage drops are going to be, so that you know if your power supply is going to be able to support that loop. And if not, you have to look to something else. You either need to get devices that are externally powered by something else other than the loop to lower their voltage drop, or you need to get a power supply that provides more voltage. Then you've got the receiver or receivers. The job of these is to receive that current signal. These are your panel meters, your chart recorders. The inputs into a PLC, the input cards on a SCADA system, essentially anything else that is reading that current loop. And usually what these will do is internally, invisible to operators or installers, they'll have some kind of small sense resistor. And using that voltage equals current times resistance equation, they can calculate out, well,
Class, the quality of video went down, I think, right? For a few moments. Class, yeah, I will repeat that part. Okay, so till that part, let us have a questionnaire. Okay, I will repeat that particular part. It was from receiver, but before that, can you answer me this question that sensor is a part of our current loop? Am I correct or not? Correct or incorrect? Answer either correct or incorrect. My statement is that sensor is a part of current loop. Yes. Most of you have answered no. And those who have answered correct, they might be confused. So let me give you another question, and through those answers, I think you will be aligned to this. Sensor is, if sensor would have been the part of current loop, okay, so was that signal useful for that particular current loop? Was that amount of sensor okay, let me take it this way. There are thermal sensors. Okay, there are thermal temperature measurement sensor. One is your thermocouple type, and one is your resistance type. Okay, so just tell me that what kind of output does a thermocouple gives? A thermocouple gives us the kind of output, whether it is change of voltage or resistance. So when there is a temperature difference, a thermocouple gives. Do you know what is a thermocouple and what is the difference between thermocouple and RTDs, resistance temperature detectors? Do you know that difference? I will go into that details if you don't know. No. Okay. No issues. I will go into that. Meanwhile, just understand that sensor is not a part of the current loop, because the type of signal that it is giving has to be you can say processed, okay, in order to be in the current loop. So that work of taking the data, or you can say taking that particular sense from the sensor and processing it and providing that output to the current loop, that work is being done by class transmitter. Yes, correct Bhanu, correct Nayan, correct Khushbu, Kalpana, Hitesh, yes Abhay. Okay, so those who have answered it that it is correct, did you got your answer that yes, sensor is not the part of your sensor is not the part of your current loop, your transmitter is the part of your current loop. Okay, so that this is a very much confusing thing, and if you are very much cognizant about it, that what is the difference between a sensor and a transmitter in a particular loop, where the sensor works, what is transmitter, how this current loop works, this is a very useful knowledge for you, a very unique kind of knowledge which can lead you to be in the upfront from various students. Okay, so let us now repeat that particular part. I think from this receiver. Yeah, from here.
And trying to run it with a 9-volt power supply. Because regardless of how small the voltage drops may be and all those other pieces of equipment, that 18 volts in your transmitter is going to sink that 9-volt supply, and now all of a sudden your system's not going to work. So it's critical, especially in cases where you're involving 2-wire devices, that you know what your voltage drops are going to be, so that you know if your power supply is going to be able to support that loop. And if not, you have to look to something else. You either need to get devices that are externally powered by something else other than the loop to lower their voltage drop, or you need to get a power supply that provides more voltage. Then you've got the receiver or receivers. The job of these is to receive that current signal. These are your panel meters, your chart recorders, the inputs into a PLC, the input cards on a SCADA system. Essentially anything else that is reading that current loop. And usually what these will do is internally, invisible to operators or installers, they'll have some kind of small sense resistor. And using that voltage equals current times resistance equation, they can calculate out, well, I have a microcontroller, say, inside of this, or some kind of simple electronics that reads the voltage drop across my small sense resistor. And that's going to allow me to calculate out what the current is. And then there's some kind of programming you usually do, such as scaling it for the display values that allow it to act on that information. Sometimes that's just displaying or recording that information. Other times you're going to have additional outputs from these receivers that could be relays for alarms, or they could be serial communication signals to your control system. It may even be an additional 4 to 20 milliamp loop that's scaled differently that goes off to some other devices somewhere. So the receiver is one of any device that is going to be on this loop, but they all have somewhat similar characteristics. You want to be aware of their input impedance, their voltage drops, and none of them are going to actually be regulating your current. That's the job of the transmitter and the power supply. One thing I'll make quick note of is that oftentimes either the transmitter or the receiver will have a power supply built into them. That's why sometimes you don't need a separate one. The panel meter you see here, for example, that's a Precision Digital ProView panel meter. If you're powering that from a separate DC or AC voltage, it includes a 24-volt power supply that's isolated from that other supply for you to use in powering up your loop. So in a case where you have a meter like this, you don't need a power supply because the power supply is built into one of your receivers. Similarly, there are transmitters that get powered by some other external supply that's not a part of the 4 to 20 loop, and therefore they use that to provide power that you can use to run your loop. The last component is something that generates a lot of questions, but oftentimes isn't really relevant. So I want to take a minute to talk about the wire that you use to run your loop. So wire does add resistance to your loop, but the resistance is extremely small. The chart here shows, based on your wire gauge, how many ohms in resistance you get of wire. So if you're using standard 12 gauge wire and you've run 1,000 feet of this, you've only got 1.6 ohms. Even at 20 milliamps, if you walk through that voltage drop is equal to current times resistance equation, you're going to see that you're going to drop around 30 millivolts off of that 1,000 feet of wire. Well, if you're using a 24 volt supply, 30 millivolts is not going to cause you a problem. And unlike a voltage signal for control systems, because current is the same everywhere in the loop, you don't get any added inaccuracy because of that voltage drop either. The same milliamps that are being put out by the transmitter are going to be the same that are arriving at your receiver, regardless of what the wire may do to resistance or voltage drops. So in a 4 to 20 system, you really don't need to be concerned about the wire unless you are running really close to that voltage cap, which is I generally recommend against anyway. And Bruce, you had a couple questions about the audience.
Yeah, that's good stuff, Joe. Thanks very much. Looks like another question for the audience, a polling.
So class, I think you now understand that what is the relevance of 4 to 20 milliamps. Okay, just a few questions about the receiver. Can you tell me that what can be the receiver in a particular current loop? What can be a receiver in a particular current loop? The receiver is someone who receives the output. What can be the receiver? Whether it is a controller or something else. Yeah, you can say speed controller, or you can say any kind of controller. Okay. So for example, you have a level tank. Yeah, controller. Okay. It can be a controller. It can be a display also. Yes, Nayan, very good. A display also can be the part of it. Yes, a controller. Yeah, correct. PLC. PLC. Correct. Very correct. Very correct. Okay. So yes, a receiver can be a controller, or you can say it can be a PLC which is connected to it. Okay. Actuator, again, Nayan, we are talking about, yeah, Hitesh, it can be a remote. It is receiving a particular signal. Okay. And the actuator will be acting after a particular, you can say, a control analogy. Okay. So you will have a particular logic, Nayan. Okay. For example, you have a tank, water tank. Okay. If the level is 0, there will be a logic that will start a particular valve. Okay, it will open a particular valve when a level is 0. Okay, so that opening and actuator, that is all the part of the components that come after the control. We are just talking about sensors right now. We are just talking about the loop that a sensor has. Okay, Nan? Okay. Okay, so we can't say that it can be an actuator valve. Okay, Hitesh, yes, remote can be the answer for this. Why? Because that is providing a signal. Okay, or you can say remote is a combination of sensor and transmitter. Can you say that remote is a combination of sensor and transmitter? Class, my question is, can we say that remote is a combination of sensor and transmitter? Yes, yes. The only difference is that the communication has been done through electromagnetic waves, or you can say light, rather than your wire connection. Okay, okay. There are a few questionnaires also, few very interesting questions that has been asked by industry people only. You can also have a look. It is just for you to have a look at what kind of questions can arise in the minds of industry people. These all are
question,
okay.
And then we'll open it up. We've got a few questions coming in via the question window that we'll take. So if something comes to mind even now, go ahead and type it in the question window, and I'll be posing those to Joe here in a minute. This poll is, what is your primary application for monitoring and or not too many waiting? Could that be noise or something related to a signal? Joe, what do you think?
Well,
Yeah,
okay,
listen from this.
Let's have some questions. We have a question from Jean-Pierre in Montreal. And his question is that he recently changed his turbidity transmitter from one that handles 0 to 1 MTU to one that handles 0 to 5 MTU over its 4 to 20 milliamp range. But he only measures from 0 to 0.15 MTU. So since then, the HMI and other equipment, his 4 to 20 milliamp signal goes or has been fluctuating. Could that be noise or something related to a signal? Joe, what do you think?
Well, just to recap there, so he had a 0 to 1 NTU, which is a turbidity unit, measuring flow turbidity. And then he changed out to a 1 to 5 unit. And I'm presuming then that his scale was 4 milliamps at 0 and 20 milliamps at 1, and then he changed it out to be 20 milliamps at 5. If he's only looking at a small portion of that range, then what is likely happening there is he has his receivers scaled such that they're only looking at somewhere between 15 to 3% of the range of his transmitter. And that would be causing him a problem. So originally, if he was looking at 15% of his range, let's say, he could afford to have some noise in that system. Whereas now that he's looking at only 3% of his range, all of his process variable ranges that he's looking at are.
So students, my question is very simple for you all regarding this question. कुछ समझ में आया आपको थोड़ा बहुत? Yes or no? What was the question? What was the answer? Class, kindly respond on the chat box. Were you able to understand what the question was? No. Okay. No issues. Oh, okay. No issue. I completely understand that. Even if I would have listened it for the first time, I would also have not got that. But that is why I am here, to just make you understand these videos. See, don't look at the specifications about what he asked. What you were afraid of was that they started talking about NTU. Just forget it. Okay? NTUs are, although for your knowledge, I can say that NTUs are net transfer units, and that is a mechanical aspect for that. But leave it. Okay? What he was saying, what the question was, that when he is changing the parameters of a particular input, or when he is changing the range of observation, the noise is getting bigger and bigger, and his 4 to 20 milliampere signal is getting fluctuated. Okay? So his question was that he has changed its process from 0 to 5 to 0 to 0.1. Okay? 0 to 5 NTUs to 0 to 0.1, he has changed the process. So the answer that Ryan gave was that you have changed your range of observation. When you are changing your range of observation, the external parameters of process are adding into your signal. That is why you are getting a greater noise level. Okay, let me repeat it. That the question was that why it is happening that my 4 to 20 milliamp output is fluctuating when I am changing my process observation from 0 to 5 to 0 to 0.1. The answer to this was that when you are changing the range of your observation, the process fluctuations are adding into your signal, and the fluctuation is more, therefore you are getting more fluctuations for a respective signal. So you need to change or alter or tune it or calibrate it according to range also. Did you get it now, or should I again repeat it? Class? Okay. So one more thing for my addition is that not always look at the specifications. Okay. हमेशा ऐसा होगा बेटा कि आपको मैनेजरियल लेवल पे भी कोई ना कोई कुछ स्पेसिफिक टर्म पे कंफ्यूज करने की कोशिश करेगा, कुछ कॉम्प्लिकेटेड से वर्ड्स के साथ आपको कन्वे करने की कोशिश करेगा. आपको केवल अपने रेलेवेंस की चीज को ढूंढना है हमेशा. ओके. हालांकि यहाँ पे उनका अपना रेलेवेंस था, लेकिन आपको एक इंफॉर्मेशन ये मिली कि आपको रेंज को भी ध्यान में रखना है. Okay, so with that note, Baki sab are all aligned to this. I only got 1, 2, 3, 4, 5 yes from Nayan, Varun, Muskan, Khushbu. Yeah, yeah. Okay, 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 okay. Because it is important for you to understand. Concepts will always be there, and there will always be data around it. There will always be a particular knowledge, but the right kind of knowledge and right kind of attitude is very important. Okay, आपको खुद एक्सट्रैक्ट करनी है नॉलेज जो आपके यूज में है, ठीक है ना? तो वो चीज बहुत ज्यादा जरूरी है. And that is my main motive, to not only transfer you technically but also transform you as an industry person.
Only really going to be varying by about a half of a milliamp. And when you have the entire range that you're trying to display or control in half of a milliamp and not the full 16 milliamp range, then yes, you become susceptible to additional noise effects. You also run the risk that minor fluctuations in the transmitter's ability to control the current or inaccuracies that are happening while the flow is being measured are going to be much more pronounced. So really the lesson there is you want to use as much of the full 16 milliamp range, the 4 to 20 range of your transmitter as you can. And that means either selecting a transmitter
Now Mr. Ryan has told us one more important thing, and that important thing is, can someone answer that what he has said, that you need to use your full range of anyone can answer. Answer can be wrong, answer can be right, it doesn't matter, but your answer is important for me. Any kind of answer is important. Yeah, use full 16 milliamps. Yes, Adarsh, thank you very much for your answer. Yes, use full range of your 4 to 20 milliamps. Okay, so when you are just observing for a short range of your 4 to 20 milliamp, so what can you do in order to use your full 4 to 20 milliamp range? What can we do? What can we do? For example, for a particular process, we are only getting the fluctuations from, you say you are getting fluctuations only from 8 to 20 milliamps, or you can say 10 to 8 to 15 milliamps. Then what you should do? Anyone can answer. Don't feel shy while answering. Yeah, increase range of observation. Very correct, Bhanu. What? Yeah, range of observation can be increased by changing the parameters in better transmitter or sensor. Very good, Adarsh. I need answers from all the students. Class, please. Answer can be wrong. Answer can be right. It doesn't matter, but your answer matters a lot, because these are very small questions that will never be put in front of you. I don't think that in your academics or your line these kind of questions are going to be asked. Even in industries it is not going to be asked, but these questions are important. Better transmitter or sensor, yes, correct. I'll start one-on-one session with all the students. If I will not get the answer, please give me the answer. Changing the external environment, yes, correct. So it is less susceptible to less noise. Yes, we can do it, but let us not say that it is susceptible to less noise. Let us just say that we are changing the external environment in order to get the range. Yes, correct, Nayan. Other students, any kind of answer is very much welcomed. I'm just repeating the names: Abhay, Adarsh, Alok, Aprajita, Bhanu, Hitendra. Your answers, please. Any kind of answer is welcomed. No issues. Yeah, increase range. Other answers, student? What is your answer? Varun, Sunidhi, Shubham, Sahil, Sachin, Raj, Nandini, Nayan, Muskan, Khushbu. Answer can be wrong. There is no issue that yes, we can change, use transmitter. We always use transmitter. We can use a different transmitter, or we can alter the parameters of transmitter. Correct, Khushbu? Correct. Change the transmitter, recalibrate. Yes, calibration can be another option. Varun Kumar, increase range. Yes, correct. Yeah, Prajita, increase range. Okay. Okay, so now what he was saying was that it is very important for you to understand that you need to utilize the full range, 4 to 20 milliamperes. Okay, now in order to utilize that, what you can change is that you have your receivers. Okay, you can change the resistance of receiver by changing the parameters. You have your transmitter there, and you can increase a certain amount of load in order to get into that particular range, or you can increase the excitation, or you can say processing, or you can say amplification of your what we say sensor, okay, through your transmitter. Okay, okay, this can be the reason for that.
That is properly sized to the range of process variable you're trying to read, or getting one that allows you to scale that range appropriately. So in his case, I'd recommend that he look into one of those two solutions.
Okay, good. Here's a question about one of the slides, Joe. This is from Thomas. He said the slide for the transmitter had acronyms UNA and OVR. Can you say what those are?
Sure, let me go back to that real quick if I can.
Sure.
Just so everyone knows what we're talking about. So in the lower right of the graphic here, you're going to see UNR and OVR. And what that just stands for is under range and over range. The 4 to 20 milliamp signal doesn't stop exactly at 4 and 20 milliamps. Most devices, most transmitters and receivers can handle an over and under of some percentage. And then that's usually going to be in the ballpark of, let's say, 5% or maybe half a milliamp. And the purpose of that is that these things tend not to be precise. You may get a 0 to 100 foot level transmitter, like the scaling example that's given here, but based on where your pumps are going to have to go at the bottom of the tank and where you calibrate the 0 to, there's a chance that you're going to actually go under the 0 that is 4 milliamps. And similarly, there's a chance you could end up going over the limit that you have set up to be your 20 milliamps. And so in those conditions, most devices have conditions they can be set up for, such as, well, if you go over 20 milliamps, I want you to set off these alarms. Or if you go under 4 milliamps, I want you to continue to display 0 and not go negative. So those over and under ranges are built into all of the devices that go into this 4 to 20 milliamp loop, and usually have different behaviors associated with them.
Okay, good. We have a question here from Mike. Mike says, what do you mean by regulate the current when you say the transmitter regulates the current?
Okay. So you have this equation of voltage is equal to current times resistance. And that would mean that your current, if I do a little algebra to it, that would mean that my current is actually going to be equal to my voltage divided by resistance. If that's the case, and your resistance is doesn't change, then you just have a current you can calculate out. So if I just build a simple circuit with a battery and a couple of resistors, I can do some basic math and tell you what the current's going to be all throughout that circuit. But this is a 4 to 20 milliamp range. That's what allows me to transmit different process variables to other pieces of equipment. That's what gives me the ability to transmit either my 0 feet or my 100 feet or my 4 milliamps to my 20 milliamps. So what the transmitter does is it regulates that current. So I've got the power supply that's just putting out as much current as it can to support whatever resistances are in the loop. But something has to be variable in there, and something needs to essentially dial in what the current needs to be. And there's current control circuitry in the transmitter that is used to regulate what current passes through the transmitter. And because current's the same everywhere in the circuit, that current that passes through the transmitter is the same current that's going through the rest of my loop.
Class, we will complete that particular question that he has asked, but it is very important for you to understand the difference between an resistance temperature detector and a thermocouple. So in order to get that what kind of outcome that we get from this discussion will be completed. Okay, so first of all, let me introduce with you with a video where thermocouple versus RTD. Okay, just have a very quick view towards this, and then please kindly be focused, because that will be very important for you to understand that how transmitter regulates a particular current. Okay, just have a look at it. So both your RTD and your thermocouple are used to measure the temperature, but the difference is between your working principle only. Just have a very close look towards the working principle. Okay. Or let us just have this video from real past. This one will be good. I have not actually searched this. I thought that you might be knowing about the temperature sensors, that what are RTD and thermocouple. I have to cover this, but let us just have a quick video recap that what are RTD and thermocouple. Basically, now the very basic thing is that in RTD the resistance changes, okay, whereas in thermocouple you get an voltage output. Okay, that is the only difference. But let us have a very quick view. Okay.
In your daily life and different branches of industries, there are many cases in which it's required to know the temperature of the environment, inside a reactor, winding of an electrical machine, and so on. Man has invented different technologies to do this. But why different technologies? This is because of different applications which make one technique better than the others for each specific case, and there's no unique way recommended for all applications. Most likely you've heard about RTDs, thermocouples, thermistors, semiconductor type elements, and so on, which will be addressed here. Before I get into details on this subject, let's see what a temperature sensor or temperature transducer is, and what does a temperature transmitter mean. Generally, a sensor or transducer is a physical device which is capable of transforming one type of process variable to my favorite signal type. To elaborate on this generalized sentence, let me give you an example. Temperature, pressure, flow, etc. are some process variables, and actually, they are physical characteristics of our real world. With modern technology, and because of tremendous advances in electrical engineering in the past century, we like to transform every measurable process value into an electrical signal, and a temperature sensor is a device which will transform the temperature into an electrical signal, no matter how tiny the amount of this signal might be. So far, I took a big first step, which was the transformation of temperature into electrical signal. Based on different sensor technologies, this signal may have different ranges, and for industrial applications, I need to have my signals limited to some universally accepted electrical signal ranges. Today, some of these globally accepted electrical signal ranges are 4 to 20 milliamps, 1 to 5 volts, 0 to 10 volts, etc. A temperature transmitter is a device which transforms the tiny output of a temperature transducer to one of these standard signal ranges. Now, let's get back to different temperature transducer technologies. RTD, or resistance temperature detector, is a device, the resistance of which varies with the temperature. Since it is a passive device, an external electrical current should be applied to it, and then the voltage drop across it can be measured. This voltage is a good indication of the temperature. When referring to such a device as passive, it means that the device needs an external current or voltage source. To state the obvious, a big amount of external current can cause power dissipation in the resistor of RTD and lead to excess heat. So to avoid this type of error, the current should be kept at a minimum level. This wiring diagram shows the simplest application of an RTD, called two-wire configuration. More accurate reading calls for three-wire or four-wire configurations. In reality, the distance between the temperature sensing point and measuring system calls for wiring, and since the real wiring has its own resistance, some measurement error sneaks in hereby. Three-wire and four-wire solutions are developed to remove this error. One of the most common RTDs is PT100, which consists of a thin film of platinum on a plastic film and shows a resistance of 100 ohms at 32 degrees Fahrenheit. Its resistance varies with temperature, and it can typically measure temperatures from negative 330 to 1,560 degrees Fahrenheit. The relationship between resistance and temperature of PT100 is relatively linear.
So class, can you answer me the question that what is the working principle of your RTD? Class, kindly answer this question. What is the working principle of RTD? Yes, the resistance changes with increase in temperature. Yes, correct. Okay, just keep this in mind. We will extend this session a little bit. We will take a break a little bit later because I need to link both of the things with the final conclusion. Okay, so just be with me for the final conclusion, then we will take a break. Just keep this in mind.
PT100 is just an example of platinum RTDs, and in the industry you may find different RTD types suitable for various applications. For example, copper, nickel iron, etc. Thermistors are temperature-dependent resistors and are widely used in industrial purposes, such as overcurrent protection, self-regulating heating elements, inrush current limiters, and so on. Thermistors can be NTC or PTC. In NTC, or negative temperature coefficient thermistors, resistance decreases as temperature rises. NTCs are commonly used as inrush current limiters. And with PTC, or positive temperature coefficient thermistors, resistance increases as temperature increases. PTC thermistors are commonly used as overcurrent protection and in resettable fuses. A thermocouple, or simply TC, is comprised of a couple of specific dissimilar wires joined together, forming the sensing point or junction. Based on physical characteristics called thermoelectric effect, when this junction is placed at different temperatures, different millivolt signals are generated, which can be interpreted as an indication of the temperature. In comparison with RTDs, thermocouples are self-powered and require no external excitation current source. Thermocouples are commonly used for furnaces, gas turbine combustion chambers, high-temperature exhaust ducts, etc. The main restriction of thermocouples is the accuracy, which doesn't make it the best solution for precise applications. Also, thermocouples need a reference measurement point called cold junction. The thermocouple junction is often exposed to extreme environments, while the cold junction is often mounted near the instrument location. Based on range of temperature measurement, sensitivity, and some other factors in each application, different types of thermocouples are available.
Now just tell me that what is the working principle for thermocouple? What is the working principle for thermocouple? Have you learned about the Seebeck effect? I think you must have learned about Seebeck's effect. Do you know about the Seebeck effect? Yeah, change in EMF with the change in temperature. Okay. So whenever there is a change in temperature, there will be an EMF generated. Thank you, Kalpana, for your answer. Class, please write this answer on the chat box. At least write it. Yeah. Yes, Kalpana, Sahil have answered. I need answers from everyone. Kindly write your answer on the chat box. Yeah, change of temperature results in production of different EMF. Yeah, change in EMF with temperature. Yeah, and vice versa. Yeah. Yes. Okay, change in temperature results into voltage. Okay, so that means that your RTD, your resistance was varying, whereas in your what we say thermocouple, you have a voltage. Okay, now just have a look at your diagram that you have sent through WhatsApp. Okay, just have a look towards that. Okay, or what should I do? I should do Yeah, I should use this diagram. Okay, so the question was asked, what do you mean when while you are saying that yes, this transmitter is regulating this particular current or voltage? Okay, so now see, whenever there will be a change in a physical phenomena, your transmitter is going to either, the transmitter can be of resistance type like RTD. So there will be a resistance that has been provided here. Okay, and that might resistance might have been transferred into it. Okay, or your sensor would have been, a thermocouple type, and it might have provided you a voltage. Okay, so what will happen here, that when the resistance is changing, when there is RTD type, then RTD type will have a voltage supply and it will provide a kind of voltage to it. Now you can see there is plus and minus sign that will be reversed in that particular direction. Now this is your voltage supply. Okay, this is your power supply. Just understand this, that power supply will try to give the maximum count of current that it can give. If there is no resistance, it can provide infinite amount of current. Okay, but the issue is that there is resistance. Okay, now this resistance has been calibrated in such a way that it will range into 4 to 20 milliamp. Now if it is a resistance type, there will be an external, you can say, power supply which will be provided to it, but it is going to give you a voltage here. Okay, and that too plus and minus, and that will alter the overall voltage in such a manner that with a particular kind of resistance which was fixed, your loop current is going to change. Okay, so this is only the altering phenomena. And when there is a thermocouple, then that voltage can be directly used as in transmitter, or it can be amplified and processed and sent to the loop. But a kind of voltage is always sent through a transmitter. Okay, okay, shall I repeat it? Have you understood it, or should I repeat it? Class, should I repeat it or have you understood it? Are you aligned to it, class? आई रिपीटेड आफ्टर ब्रेक. अगर कंफ्यूजन भी है तो मैं ब्रेक के बाद भी बता सकता हूँ. ब्रेक आपको टाइमली दे दूंगा, बट कंफ्यूजन है तो यस और नो में जवाब दे दो प्लीज. ओके, I'll repeat it. Okay, I'll repeat it. Okay. Let us just have a very, also should I repeat it after break? Shall we take a break or should we repeat it first? Repeat after break. Okay, definitely. Okay. So we will take a break of 15 minutes. Let us meet at 3:55. Or let us meet at 4. Okay.